Hello and welcome to the Week 12 Math 2419 weekly review. In this review, we'll mostly be covering a lot of different tests for convergence and divergence that can be applied to power series. And we'll start with the telescoping series test, then move on to geometric series, then integral test, then the direct comparison test, the limit comparison test, and finally the alternating series test if we still have time. So there's a lot to cover, so let's jump right in. Right. First off, the telescoping series test. So we'll start with just what a telescoping series is. In a telescoping series, basically successive terms try to cancel. And this tends to happen most frequently with series that can be rewritten using partial fractions. So, for example, will really help to clarify what exactly a telescoping series looks like. Let's say we have the sum from n is 1 to infinity of 1 over n times n plus 2. Well, we could rewrite this 1 over n times n plus 2 term using partial fractions, and when we do that, we get a over n plus b over n plus 2 is equal to 1 over n times n plus 2. So then a times n plus 2 plus b times n is equal to 1. And we get that a is equal to 1/2 and b is equal to negative 1/2. I'm glossing over some of the details of doing partial fractions because this is about the telescoping series test, but you can essentially rewrite the sum as the sum from n equals 1 to infinity. Now we have 1/2 times 1 over n minus 1/2 times 1 over n plus 2. And since this 1/2 is basically a coefficient of each of our terms, and it's a constant, we can pull it actually out of our sum. So I'm going to go ahead and do that now. And here we have 1 over n minus 1 over n plus 2. Now if we actually started writing out some terms of the series, our first term would be 1 over 1 minus 1 over n plus 2 is 3, plus 1 over 2 minus 1 over 4, plus 1 over 3 minus 1 over 5. We'll do one more, plus 1 over 4 minus 1 over 6, and so on. And if you look very carefully, you can actually notice that right here we have a negative 1/3, and it'll cancel exactly with this positive 1/3. Similarly, here we have a negative 1/4, and it'll cancel exactly with this positive 1/4. And it's not written, but we would actually also have a positive 1/5 to cancel with that 1/5, and a positive 1/6, and so on. So all the terms will actually end up canceling except for this one and this 1/2 right here. So we can say that this is exactly equal to the sum of 1/2 times 1 plus 1/2, which gives us 3/4 as our total sum. So just some tips for solving telescoping series. You might want to consider a telescoping series if you might have something that's a part that could be simplified using partial fractions. And once you've written it out using partial fractions, just write out the first few terms and try and see what will cancel. If we look at a weirder looking telescoping series, and I don't think you'll see anything similar to this in class, but I happen to really like this series. say we have the sum from n is equal to 2 up to infinity of the natural log of 1 minus 1 over n. Well, we can actually, focusing on this natural log of 1 minus 1 over n, we can rewrite that by combining our two middle terms as the natural log of n minus 1 over n. And then using log properties, that's the natural log of n minus 1 minus the natural log of n. So then we can rewrite our sum like so. Natural log of n minus 1 minus the natural log of n. Our first is going to be natural log of 2 minus 1 is natural log of 1 minus natural log of 2 plus the natural log of 2 minus the natural log of 3 plus the natural log of 3 minus the natural log of 4, and so on. And what you'll see is here we have negative natural log of 2 cancels with positive natural log of 2. Negative natural log of 3 cancels with positive natural log of 3. And this is actually a bit tricky to consider because the last term of the last part of one term cancels with the first part of the next term, which means what we're left with is essentially the first part of the first term and then the last part of the second term, or the last part of the last term. So for very large n's, that wouldn't be the natural log of 4, it would be minus the natural log of n. So our series would come out to be the limit as n goes to infinity of the natural log of 1 minus the natural log of n. Natural log of 1 is just 0, but then the natural log of n goes to infinity, so that goes to negative infinity, and our series diverges. That's just a neat example of a telescoping series. So go ahead and do one quick practice problem. Try this on your own. Find the exact sum of the series equal to 1 to infinity, and this is basically going to be one of the more basic telescoping series out there. Go ahead and try and find the sum. All right, let's go ahead and go over this. First off, we'll rewrite using partial fractions. So then we get that a times n plus 1 plus b times n is equal to 1. We get that a is equal to positive 1 and b is equal to negative 1. So we can rewrite our sum as the sum from n is 1 to infinity of 1 over n minus 1 over n plus 1. And when we start writing out some of our terms, our first term is 1 minus 1 half. Our second term is 1 half minus 1 third. Our third term is 1 third minus 1 fourth, so on. And our 1 halves will cancel, our 1 thirds will cancel. And once again, we're left with the very first part of the first term and the very last part of the last term. So we can rewrite that as the limit as n goes to infinity of our very first part of our first term minus the very last part of our last term. And as n goes to infinity, of course, 1 over n goes to 0, so we're left with just 1 as our result. Cool. That's it for telescoping series. So now we can move on to geometric series. Okay, and geometric series are actually going to be another kind of series where we can find the exact sum, which isn't the case for most series. Basically, a geometric series has the form sum from some starting value to infinity of a coefficient a times some ratio r to the power of n. And we say that it converges if if the magnitude of r is smaller than 1. In fact, we can find the exact sum, and it is a over 1 minus r. And in this case, a is just your first term, and r is your ratio. So let's go ahead and do an example. Let's say we have the sum from n is 0 to infinity of, go with 1 half the 2n. Well, in this case, our first term a is equal to 1 half times to the power of 2 times 0, which is 1 half to the 0th power, which is equal to 1. Now our ratio, you might think is 1 half at first, but it's actually not because we have this 2n up here. Our ratio is based off of what happens when we have just one n, so we can rewrite 1 half to the 2n as 1 half squared to the n, which is then equal to 1 half squared is 1 fourth to the n, so our ratio is actually equal to 1 fourth. Then we can find our sum by using our geometric series formula and say our sum is equal to a, which is 1, over 1 minus our radius 1 fourth. That gives us 1 over 3 fourths, so our sum is 4 thirds. Cool. Another example, let's say we have the sum from n is equal to, not infinity, from n equals 3 to infinity of 4 times 2 thirds to the n. Well, our sum is going to depend only on our first term and our radius. And we'll actually start with the radius because in this case it's a bit easier to pick out. Since it's currently just raised to the nth power, we don't need to do anything to it. You can just look at it and say, boom, 2 thirds is our radius. A is going to be our first term. So our first term is where n is equal to 3. So we simply plug in 3 for n, and we get that a is 4 times 2/3 cubed, which gives us a first term of 4 times 8 over 27, which gives us 32 over 27 as a first term. Then our exact sum is our first term, 32 over 27, over 1 minus 2/3, where 2/3 is our radius. And if we simplify that, we get 32 over 27 over 1 over 3, which gives us 32 over 9 as a final answer, I believe. Yes, yes. And that's a geometric series. So a couple of practice problems. Go ahead and find out the exact sum. N equals 2 to infinity of 1/2 times 1/4 to the nth. And secondly, the sum from n is equal to 0 to infinity of 4/3. That's a 4 to the nth. And I'll give you a minute or two to work those out. All right, let's go ahead and go over these. In our first one, our first term a is equal to 1/2 times 1/4 squared, which gives us 1 over 32 as a first term. And our radius, again, we don't need to do anything fancy to it since it's already to the nth power. It's just 1/4. So then our sum is our first term, 1 over 32 over 1 minus our radius, and that gives us 1 over 32 over 3/4, which is 1 over 32 times 4 over 3, which gives us 1 over 24 as our final answer. In our second one, well, if we look at our radius, it's actually 4/3, and if you recall, in order to converge, the magnitude of our radius has to be smaller than 1. And because 4/3 is not smaller than 1, we say that our series must diverge then. Very straightforward. Okay, Next topic is the integral test. And hidden inside this one, we're actually going to talk about the p-series test as well. So let's see the bin. And it's based off of well, you can say if your function f is positive, continuous, and also decreasing, so all three of these need to be met, then you can say that the sum from n is 0 to infinity of your sequence a sub n and the improper integral of f of x dx either both converge or they both diverge. And in this case, the n is equal to 0 and your lower bound on the integral of 0, they would both just be your starting. So if you're in, so if in your sequence you had, in your series you had a starting term of n is equal to 5, that would be the lower bound on your integral as well. So let's do a quick example. So we have the sum from n is equal to 0 to infinity of 1 over n squared plus 1. Well, because 1 over n squared plus 1 is positive, it's also continuous and decreasing, so we can use the integral test. Then we can take the improper integral from 0 to infinity of 1 over x squared plus 1, and because it's an improper integral, we have to rewrite it using a limit statement. The limit as b goes to infinity, integral from 0 to b of 1 over x squared dx plus 1 dx. This integral, if you recall, is arctangent. So that would be arctangent of x from 0 to b. And the arctangent of 0 is 0. And the limit as arctangent goes to infinity is actually pi over 2. Now, importantly, pi over 2 is not the sum of our series. We say that pi over 2 would be this improper integral from 0 to infinity of 1 over x squared plus 1 dx. And what that tells us is this improper integral converges, which then tells us that our series must converge. We can't say anything about the exact sum of our series, only that it actually just converges. That is the integral test. So we'll go ahead and go with a couple of practice problems. And we'll actually do them. There. And I'll give you a couple of minutes to work that out. All right, let's go over this. So with this first one, e to the negative n is positive, continuous, and decreasing. So we can take the limit as n goes to infinity, integral from 0 to b. Oops, sorry, I should make that a b. The limit as b goes to infinity of e to the negative x dx, which gives us the limit as b goes to infinity of minus e to the negative x, 0 to b. The limit as b goes to positive infinity of minus e to the negative infinity is 0, so then you would have minus negative 1, which gives us positive 1, and that tells us that our series then must converge. With our second one, again, we would have to rewrite as an improper integral, limit as b goes to infinity times d, since our first term or sequence in our series is 1 over x dx, and that gives us the limit as b goes to infinity of the natural log of x from 1 to b. Now, the limit as natural log goes to infinity is actually infinity, so in this case, our improper integral will diverge. And finally, for our last one, we have the limit as b goes to infinity, integral from 1 to b of 1 over x squared dx, which is the limit as b approaches infinity of minus 1 over x from 1 to b, which is 0 minus negative 1, which is 1, and that tells us that our series will converge. Now you'll notice that these last two problems are actually pretty similar, and this is where another series test comes in called the p-series test. And it's basically one specific instance of the integral test. Basically, it says if you have a power series that looks something like 1 over n to the power of p, well, this series converges whenever p is bigger than 1, and it diverges whenever p is smaller than or equal to 1. And this is known as the p-series test. But again, it's basically just the integral test in one specific application. But it's good to mention, and if you just have this memorized, it can save you a lot of trouble of solving integrals later on. Okay, but that's it for the integral test. Now we'll go ahead and move on to a couple of comparison tests. First off, the comparison test. And the direct comparison test is basically like the comparison test for improper integrals. We'll go ahead and spell it out in more explicit terms. So let's say you have a couple of positive sequences, a sub n and b sub n, and b sub n is always bigger than a sub n. Well, then you can say that if your smaller series, let's see, your smaller series is going to converge if your larger series converges. And your larger series will diverge if your smaller series diverges. And this makes sense logically because of course if you have a smaller thing that's infinite, well then your bigger thing would also have to be infinite. And if your smaller thing is, I guess, yeah, if your smaller thing is infinite, then your larger thing would also have to be infinite in order to keep up. Um, so for example, we can take the series sum from n is 1 to infinity of 1 over n squared times 2 plus cosine of n. Well, if you look very carefully, you can actually find a much simpler series. Say, well, I noticed that 1 over n squared times 2 plus cosine of n. This 2 plus cosine of n bit is always bigger than or equal to 1. So I can say that 1 over n squared times 2 plus cosine of n is always smaller than or equal to 1 over n squared. Well, by the p-series test, the sum from n is equal to 1 to infinity, 1 over n squared converges. As I said, by p-series, but we'll just write it down. Well, because 1 over n squared is bigger, and it converges to a real number, their smaller series can't be infinite because then it would be larger. So then we can say by the direct comparison test, our sum from n is equal to 1 to infinity of 1 over n squared times 2 plus cosine of n must also converge. Okay, and just one practice problem for this one. Determine the convergence of this series. Sum from n is equal to 1 to infinity of 1 over n factorial. And I'll give you a couple of minutes to work on that. All right, let's go ahead and go over this one. So in this case, we can actually look at n squared again and say that n squared is actually smaller than n factorial whenever n is bigger than or equal to 3. Nope, not 3, whenever n is bigger than or equal to 4. There we go. So then that tells us that 1 over n squared is always bigger than or equal to 1 over n factorial where n is bigger than or equal to 4. Which means we can again take the sum from n is equal to 1 to infinity of 1 over n squared and say this converges. So because it's always bigger than our 1 over n factorial sum term whenever n is equal to 4, we can actually get the sum from n is equal to 1 to infinity of 1 over n factorial converges. And you might be wondering where this 4 comes into play. And it actually doesn't make a huge difference because we can rewrite the sum from n equals 1 to infinity of 1 over n factorial as the sum from n is equal to 1 to 3 of 1 over n factorial plus 1, the sum from n equals 4 to infinity of 1 over n factorial. And we know that this part here must converge by the direct comparison test to 1 over n squared, because this 1 over n squared is always bigger than 1 over n factorial on this whole series. And we know that this little series must also converge because it's a finite sum. It's just 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. And we know that that converges to a real number. So then the sum of two finite series is, of course, finite. So then we get that our total series converges. The sum of two finite positive series is convergent. All right, well, that's it for the direct comparison test. Next up is the limit comparison test, which is probably my favorite power series tests. So the limit comparison test. And the limit comparison test is really useful for getting rid of extra parts of power series, so like coefficients, smaller terms. So like if you had a 5n plus 5 in there, you could reduce it down to just like an n using the limit comparison test. That's what it's good for. So it's really good for helping simplify your problem. And we'll start with a formal definition. Let's say you have two sequences, and they're both positive. And also, you can take the limit as n goes to infinity of the quotient of these two power series, these two sequences. And when you take that limit, you get a real number L. And this limit, importantly, is not equal to 0, and it's not infinite. Well, once you find this limit, you can know that your sum of a sub n and your sum, I cannot write. Basically, if you get this L, a real number that's not 0, then your two power series would have to both converge or both diverge. Let's go ahead and do an example problem. Let's say you have the sum from n equals 1 to infinity of 1 over e to the n minus n squared. Well, I'm going to let a sub n just be this power series, 1 over e to the n minus n squared. And then I'm going to let b sub n basically just be the largest term from a sub n. In this case, it's just going to be 1 over e to the n. Then I can take the limit as n goes to infinity of a sub n over b sub n, which gives me 1 over e to the n minus n squared over 1 over e to the n, and that's e to the n over e to the n minus n squared. And as n approaches infinity, this minus n squared basically becomes irrelevant, and we get a limit of 1. Well, since 1 is not equal to 0 and it's not infinite, then we know that either the sum from n is equal to 1 to infinity of 1 over e to the n will basically, this power series has the same convergence as our original power series. And we can actually say that this series converges by the geometric series test, because we can rewrite it as 1 over e to the power of n, and 1 over e is smaller than 1, so that will actually converge. And because this comparison series converges, we can then say that our overall series converges as well by the limit comparison test. All right. We'll go ahead and do a practice problem. Just one for this one. Sum from n is equal to 2 to infinity of 1 over 2n squared minus 2. I'll give you a couple of minutes to work on that. Let's take a look at the solution now. So by using the limit comparison test, we can compare this series to a series that basically has the similar components, just with a lot less extra bits added. So if you look at this original power series, we can notice that the main component is this n squared. It's the largest term. So we're actually going to use a comparison with just this series 1 over n squared. Well, we can take the limit as n goes to infinity of 1 over 2n squared minus 2 over 1 over n squared, which is the limit as n goes to infinity of just n squared over 2n squared minus 2. And we just look at the coefficients of the largest terms because it's balanced, and we get 1/2. And because this limit is not equal to 0 and it's not infinite, we know that either the sum from 1 over the sum of 1 over n squared and our original sum will both converge or both diverge. Well, we know that the sum from 2 to infinity of 1 over n squared must converge by the p-series test. So because we applied the limit comparison test and found a real limit, we know that the sum from n equals 2 to infinity of 1 over 2n squared minus 2 must also converge. Cool. Now, moving on to the last topic for today, the alternating series test. This is an interesting test. It's useful in many situations. And I guess we'll start with the definition of alternating series. An alternating series is a series where terms alternate in sign. They switch from positive to negative and positive to negative and so on. And as a quick example, the series -1 to the n is alternating. And that's just a really easy series. Now, the alternating series test has 3 conditions. We can say that the sum from n equals 0 to infinity of a sub n, excuse me, we say that this sum converges if these 3 things are met. First off, it has to be alternating. Second, each term has to be smaller than the one that came before it. And mathematically speaking, we write that the next term, a sub n plus 1, is smaller than the current term, a sub n. And lastly, terms in the sequence have to go to 0. So let's do an example. Say we have the sum from n equals 1 to infinity of -1 to the nth over n. And we saw previously in the way back in the integral test that the non-alternating version of this, the sum from n equals 1 to infinity of 1 over n, diverged. But what about the sum when it is alternating? Well, first off, it meets our first condition. It's alternating because of this -1 to the n. Second off, we can see that 1 over n plus 1 is smaller than 1 over n, because we can always cross multiply, and we see that n is smaller than n plus 1 whenever n is positive. So that's true, I guess, for all n's. And finally, we can take the limit as n goes to infinity of minus the n over n, and that gives us 0. So the alternating series test then tells us that our series will converge. And there is one other thing we should talk about, and that's conditional convergence versus absolute convergence. You'll notice that when we took the absolute value of this series, which came out to be this 1 over n, it diverged. So because the non-alternating version of the series diverges, we say that the alternating series converges conditionally. Um, if we'd instead taken the series sum from n equals 1 to infinity of minus 1 to the n over n squared, well, we saw that the non-alternating version of this series actually converged. And this alternating version also converges, but because the non-alternating version also converges, we say that this series converges absolutely. And that's the difference between conditional convergence and absolute convergence. A series converges conditionally if it has to be alternating to converge, and it converges absolutely if the non-alternating version will converge. All right, so go ahead and do one practice problem. Convergence of this series here. That should be a times n squared minus. There we go. I'll give you a minute or two to work on that. All right, let's go over this problem. First off, we can see that this is alternating. If we look at the cosine of n pi part, that's actually what makes it alternating. Because when n is even, that would give us positive 1, and when n is odd, that would give us negative 1. So that's the part that makes it alternating, and you might see that in some of your classwork. Now we can also see if we take an n plus 1 term, we can see that that is actually smaller than the n term. Because first off, we can cross multiply, we get e to the n times n plus 1 squared is less than or equal to e times e to the n times n squared. Cancel e to the n's on both sides, and we get n squared plus 2n plus 1 is smaller than en squared. And this is true because the coefficient on our n squared on the right-hand side is larger than the coefficient for our n squared term on the left-hand side. So it's going to be larger for some n value that's as n approaches infinity. So this condition is true as well. Finally, we can see that the limit as n approaches infinity of n squared over e to the n does in fact approach 0. So all three conditions for our alternating series test are met. So we can say that our series converges by the alternating series test. If we wanted to determine absolute versus conditional convergence, we do have a couple of options. I think the one you haven't, let's see, I would probably approach this one using the limit comparison test. You could simply compare it to the series 1 over e to the n, because then your n squared is insignificant when compared to your e to the n. You may also want to consider approaching this using what's called the ratio test, which you'll learn about next week. But in this case, it does turn out to converge absolutely. If you want to verify using the limit comparison test, you're welcome to, but it does converge by the alternating series test. That's all that I've got for today, so thanks for coming by and have a nice week.